In this lecture video, we start looking at multivariate analysis of variance, or MANOVA. Now you'll recall that multivariate analysis of variance is a multivariate generalization of univariate analysis of variance. And if you think back to your first two methods classes, you'll recall that univariate analysis of variance is a procedure that we use to compare the means of a given response variable across two or more populations. Now in this setup, we have m populations under consideration, m being greater than or equal to 2. Population 1 has a mean vector mu sub 1 and a covariance matrix of cap sig sub 1. Population 2 has a mean vector mu sub 2 and a covariance matrix cap sig sub 2, and so on down to population m with a mean vector of mu sub m and covariance matrix cap sig sub m. The null hypothesis to be tested in a multivariate analysis of variance is that the mean vectors of the m populations are all equal. And so that's expressed this way in vector notation. And for right now, I'm going to denote the alternative hypothesis as the complement of the null hypothesis, which it always is because the null and alternative hypotheses are logical complements. But for now, notationally, I'm just going to represent it this way. But in words, we can describe the alternative hypothesis as that at least one of the mean vectors is different than the others. So again, the null hypothesis is that the mean vectors of the m populations are all the same, they're all equal. The alternative is that at least one of the mean vectors is different than the others. Now let's look at the structure of a mean vector and remind ourselves what it looks like. In this notation, I'm going to let j represent the population that we're talking about, and so j goes from 1 to m. And the mean vector for the jth population, which is mu sub j, is a p by 1 vector. Remember, it's a p by 1 vector because we're dealing with p by 1 random vectors, so there are p random variables, p response variables that we're measuring on each experimental unit. And so the first entry in this in mu sub j is mu sub 1j. The second entry is mu sub 2j, and so forth down to the last entry, mu sub pj. And these are the means of the corresponding response variables for the jth population. So mu sub ij is equal to the expected value of x sub kij, where x sub kij is the ith response variable for the kth experimental unit from population j. So again, the mean vector for a given population is just the vector containing the means of the p response variables for that particular population. Now, there are some other equivalent ways of expressing the null and alternative hypotheses that are being tested by a multivariate analysis of variance. And so one way is to express the null hypotheses, and again we're still using vector notation. But if I go back to this statement right here a couple slides back, so mu1 equal to mu2 equal to, and so forth, out to mu sub m, that's actually several different statements simultaneously. In particular, it is m minus 1 statements put together or logically connected with a logical and. And so that null hypothesis is equivalent to this statement, mean vector mu sub 1 equal to mu sub 2, and mu1 is equal to mu sub 3, and so forth out to the last one, the last equality, mu1 equal to mu sub m. So the null hypothesis 2 slides back, right here, is true if and only if this null hypothesis is true. Therefore, they are logically equivalent. And so if we think of the null hypothesis in this way, then we can express the alternative hypothesis, which is the logical complement of the null hypothesis. We can express the alternative using vector notation this way. Either mu1's not equal to mu2, or mu1's not equal to mu3, or, and so forth out to, or mu1's not equal to mu sub m. So that's a very useful way to think about the hypotheses that are being tested by a multivariate analysis of variance. Now, another way to think about the null and alternative hypotheses, and again, these are equivalent ways of thinking about the hypotheses, equivalent with the first two approaches or the first two representations that we've given. So in this setup, the null hypothesis is equivalent to saying that mu sub 1, 1 is equal to mu sub 1, 2, and so forth out to mu sub 1m, and mu sub 2, 1 is equal to mu sub 2, 2 is equal to, and so forth out to mu sub 2m, and so forth, and we all get all the way down to the components for the pth response variable, mu sub p1 equal to mu sub p2, and so forth out to mu sub pm. So this is another way to express the null hypothesis, and this is equivalent to the original representation. If we think of the null hypothesis in this way, then we can think of the alternative hypothesis, which again is the logical complement of the null, in the following way. Now, I am expressing the complement of this statement here using complement notation that you might be familiar with from your first methods classes. So the alternative to that null hypothesis would be that either this set of equalities is not true, or this set of equalities is not true, or, and so forth, down to the possibility that this set of equalities is not true. And so again, looking at the details, looking at what these hypotheses represent in terms of the individual components within the vectors is very helpful in several ways. Okay, now let me just go back here. We can expand this statement a little bit further, okay? So bear with me here. We're going to, what we're doing is we're expanding these statements more and more until we get them fully expressed in terms of the individual components of all the vectors. And that, like I said, that's going to be very helpful for a couple different reasons. But we can expand this a little bit further, all right? So that this statement here, this string of equalities, is true if and only if this statement is true. And so, and then let me go back here. Then this statement is true if and only if this statement is true. And so let's look at this. The null hypothesis, the original null hypothesis, and the null hypothesis in the previous setup is equivalent to the following. That mu sub 1, 1 is equal to mu sub 1, 2, and mu sub 1, 1 is equal to mu sub 1, 3, and then so forth, all the way out to the mth population. Mu sub 1, 1 is equal to mu sub 1m. That's logically connected with an and to the following as well. So mu sub 2, 1 is equal to mu sub 1, 2, or mu sub 2, 2, and mu sub 2, 1 is equal to mu sub 2, 3, and so forth out to, and mu sub 2, 1 is equal to mu sub 2m. And then so forth, and then all the way down to the last response variable, means. So mu sub p1 is equal to mu sub p2, and mu sub p1 is equal to mu sub p3, and so forth, and mu sub p1 is equal to mu sub pm. So you'll notice here that what we've done here is we have expressed the null hypothesis in terms of every single component in every single vector. Okay, so when we think about what the null hypothesis represents, in fact, let me go back all the way to this statement. This is definitely an abbreviation for what's actually being tested by that null hypothesis. All we see here, a lot of the detail is hidden. Really, all we see are the m mean vectors. But when we expand it out and we look at this null hypothesis with all the components exposed, we see that there's a lot going on here in this null hypothesis. The corresponding alternative hypothesis would be that mu1 is not equal to mu sub 1, 2, or mu sub 1, 1 is not equal to mu sub 1, 3, or, and so forth, out to mu sub 1, 1 not equal to mu sub 1m, or mu sub 2, 1 is not equal to mu sub 2, 2, or mu sub 2, 1 is not equal to mu sub 2, 3, or, and so forth, or mu sub 2, 1 is not equal to mu sub 2m, or, and then and so forth all the way down to, or mu sub p1 is not equal to mu sub p2, and this should be or. I've got a typo there, so let me fix that. Okay, so that's been fixed. So then we're looking at this last set of possibilities. Mu sub p1 is not equal to mu sub p2, or mu sub p1 is not equal to mu sub p3, or, and so forth out to, or mu sub p1 is not equal to mu sub pm. So in other words, at least one of these, this is the opposite. The null hypothesis here says that all of these equalities are true. The complement, or the alternative, says that at least one of these equalities is not true, and that's the long way to write this. So we can see here that, one of the reasons that I'm showing you this detail is because it's very helpful. We need to really understand, everything that's being tested here in the context of a MANOVA. If we just express it using vector notation or in some kind of a verbal or textual description, then a lot of this detail may be overlooked. But if we look at the detail like this, it really helps us to see what is actually being tested. Okay, so now let's look at one other way, and I think this is kind of a handy notational way to look at this. So for each response variable, I going from 1 to p, so again, we've got p response variables, and here I'm letting I correspond to or represent the particular response variable that we're looking at. So I goes from 1 to p. And let's okay, so let's let, for I going from 1 to p, let's let h sub oi be the statement that mu sub I1 is equal to mu sub I2 and so forth out to mu sub im. And so what this is saying is that for the ith response variable, the means of that response variable are the same across the m populations. And so we can think of this as the null hypothesis in a univariate analysis of variance for the ith response variable. Likewise, h sub 1i would be the logical complement or the opposite of this. And so h sub 1i would be the alternative hypothesis in a univariate analysis for the ith response variable. And so that is what we're saying down here. Now, with that notation, expressing these somewhat involved hypotheses, just representing them this way, then we can restate the null and alternative hypotheses for the MANOVA in terms of the individual univariate ANOVA hypotheses in the following way. And so the null hypothesis for the MANOVA, the multivariate analysis of variance, would be that the null hypotheses for the univariate ANOVAs are all equal against the alternative hypothesis. This is the alternative hypothesis for, again, the MANOVA, the multivariate analysis of variance. It is the opposite of this statement, and the opposite of the null hypothesis is that at least one of the alternative hypotheses is true for the univariate analysis of variances. So, in other words, for at least one of the response variables, the alternative hypothesis of the ANOVA for that response variable is true. So this is another way that we can represent the null and alternative hypotheses for the multivariate analysis of variance. Now, one of the reasons that it's helpful to look at these various ways of expressing the null and alternative hypothesis for the MANOVA is because, if we get a significant MANOVA, in other words, if we, based on the data, reject the null hypothesis of the multivariate analysis of variance, then the question is, what do we do? Are we done? Do we stop? And the answer is no. Actually, the work is just beginning. If we reject the null hypothesis for the multivariate analysis of variance, then we have several ways that we can follow up on that multivariate analysis of variance. And the way that we choose to follow up may depend on the way that we've chosen to think about and represent the null hypothesis of that multivariate analysis of variance. And so if we, let me just go back here and say, let's suppose that we chose to represent the null hypothesis for that multivariate analysis of variance in this way. All right, that mu1 is equal to mu2 and mu1 is equal to mu3 and so forth out to mu sub 1 equal to mu sub m, against the alternative that at least one of those pairwise comparisons is not true or is not equal. And so what we could do then, let's suppose that that is the way that we choose to represent the null and alternative hypotheses. So if we reject the null hypothesis in that setup, then we're concluding that for at least one pair of the populations, the mean vectors are not equal. And so the natural follow-up would be to perform pairwise comparisons at the multivariate level. And so we would compare populations 1 and 2, all right, using these hypotheses. And now keep in mind, notice that these mu's are bolded. So these are vectors, and so this is a multivariate pairwise comparison. All right, and so we would compare compare populations 1 and 2, the mean vectors of populations 1 and 2. We would compare the mean vectors for populations 1 and 3, and so forth, until we get out to comparing the populations 1 and population M. And then we would compare populations 2 and 3, populations 2 and 4 in this way, and so forth, until we get out to the last comparison, comparing the mean vectors for populations M minus 1 and M. Now, as you'll remember from your first two methods classes, when you did a univariate analysis of variance, one of the ways that you followed up a significant ANOVA was to perform all pairwise comparisons. All right, and that's essentially what we're doing here. The only difference is we have vectors that we're comparing instead of scalars, and so we are performing multivariate pairwise comparisons. Now, if we follow up the significant MANOVA in this way, then we've got m times m minus 1 over 2 multivariate pairwise comparisons to perform. Okay? So now, what do we do if any of these multivariate pairwise comparisons are significant? Well, if a multivariate pairwise comparison is significant, then at that point what we can do is drop down to the univariate level, and for each response variable, perform a univariate pairwise comparison involving the two populations in question. Now, when we do that, for that given pair of populations that we're comparing, there will be p pairwise comparisons, univariate pairwise comparisons, one for each response variable. So, for example, if we were to perform the pairwise comparison of populations 1 and 2, again at the multivariate level, and if we were to reject that null hypothesis and conclude that mu1 is not equal to mu2, well, that means that for at least one of the response variables, the two population means are not equal. And so then the question is, well, which population mean, or for which response variables for which response variable are the means not equal? And then that's why you would drop down and do things at the univariate level. So that's one approach. If you get a significant multivariate analysis of variance, then do multivariate pairwise comparisons. And if any of those pairwise comparisons are significant, then drop down to the univariate level and do univariate pairwise comparisons, one comparison for each response variable. Now, another approach, another way to follow up a significant MANOVA is to immediately drop down to the univariate level and perform separate univariate ANOVAs for each of the p response variables. Now, let me just go back and show you if we were to think of the null hypothesis of the MANOVA in this way, or equivalently in this way. Okay? And if you look at this, this first statement, this is the null hypothesis of the univariate analysis of variance for the first response variable. This is the null hypothesis for the analysis of variance for the second response variable, and so forth down to this statement, which is the null hypothesis for the analysis of variance for the pth response variable. Okay, so if we think of the null hypothesis of the MANOVA in this way, then it makes sense then to use this approach here. If we were to reject the null hypothesis of the MANOVA, then thinking about it in this particular way, the conclusion would be that for each one of the, or for at least one of the response variables, the univariate analysis of variance is significant. And so the question is, for which response variable? And so what we would do is for each response variable, for each of the p response variables, we would perform a univariate analysis of variance. And so here are the hypotheses for the univariate ANOVA for response variable 1. All right, we would also perform a univariate ANOVA for response variable 2, and so forth down to the last response variable p. We would perform a univariate ANOVA for that response variable as well. And so again, the follow-up here, the initial follow-up, and remember there are really two levels of follow-up. The first stage of the follow-up is once we have a significant MANOVA, then if we've thought about the hypotheses of that MANOVA in terms of individual univariate ANOVAs, and when we reject it, we're immediately going to drop down to the univariate level. In the preceding procedure that we looked at, we stayed at the multivariate level and did pairwise comparisons. In this approach, we're following up that significant MANOVA by dropping down immediately to that univariate level and performing a univariate ANOVA for each of the p response variables. And in doing that, there are going to be p univariate ANOVAs for us to perform. Now, for a given univariate ANOVA, if it's significant, then the natural follow-up would be to perform pairwise comparisons for that particular response variable. And if we do that, then for that part of the procedure, there are m times m minus 1 over 2 univariate pairwise comparisons. Okay, so again, we've got really two different approaches to following up a significant MANOVA. The first approach we looked at was staying at the multivariate level and doing pairwise comparisons among the m populations. If any of those multivariate pairwise comparisons are significant, then we, at that point, drop down to the univariate level and do univariate pairwise comparisons. A pairwise comparison for the two populations in question for each response variable. The second approach to following up a significant MANOVA is to immediately drop down to the univariate level, do univariate ANOVAs for each response variable, and then for a given response variable, if its ANOVA is significant, in other words, if we conclude that for that variable the population means are not all equal, right? At least one of the populations has a different mean than the others, then the natural follow-up is at that point to do univariate pairwise comparisons. All right. So now let's look at the data for the analysis. And so for population J going from 1 to m again, let x sub 1j, x sub 2j, and so forth out to x sub nj be a random sample of size n sub j from population J. Well, there's a lot of j's going on, isn't it? Well, so n sub j is the sample size that we obtain from population J. So n sub 1 is the size of the random sample we get from population 1. N sub 2 is the size of the random sample we get from population 2, and so forth, out to n sub m, which is the size of the sample we get from population M. And so specifically, if we want to show these, if we want to write all these out so we can just see them, okay, this is what the data vectors would look like. And again, these are vectors. Each of these is a p by 1 vector because each of these vectors contains p response variables, the p measured response variables on each experimental unit. Now, again, we're saying that each of these, in a sample or from each population, we get a random sample. And you'll remember that what that means is that the response vectors, the random vectors, are independent and identically distributed. So they're identically distributed, they all come from the same population, and they are stochastically independent. In addition, the other assumption that is part of MANOVA is that the samples from different populations are stochastically independent as well. And so therefore, not only are the vectors within a sample independent, but the samples, or I'm sorry, not the mean vectors, but the vectors across samples are independent as well. So all of these vectors are assumed to be stochastically independent of each other. So that's a very important assumption that we need to remember and take into consideration. And you'll recall that independence really follows from the way that we perform the experiment. So if an experiment is done in such a way that the vectors from a given population are not independent, then we really should not use MANOVA or use this procedure, because this procedure assumes, it has built into the mathematics of its procedure, that the vectors are all stochastically independent. Okay, so let's look further at the assumptions that are built into a multivariate analysis of variance. Now let me say, well, we'll call it a standard multivariate analysis of variance. When I say that, what I mean is the way that most MANOVA procedures are coded or programmed into statistical software would correspond to what we're calling the standard MANOVA procedure. And so for the purposes of analysis, in order to draw inferences, for example, making or testing hypotheses, perhaps constructing confidence regions, the populations are assumed to have a multivariate normal distribution. So the random sample from population 1 has a multivariate normal distribution with mean mu sub 1 and a covariance matrix cap sig. The random sample from population 2 has a multivariate normal distribution with mean vector mu sub 2 and a covariance matrix of cap sig, and so forth down to the mth population. The random sample from population M, again, is assumed to have a multivariate normal distribution with mean vector mu sub m and covariance matrix cap sig. Now, I just want to point out here that the standard MANOVA procedure assumes, or has built into it, the assumption that the covariance matrices are the same for all M populations. Notice that we've not subscripted the cap sigs with subscripts like we did initially, okay, because in this standard procedure, the way that it's programmed into or built into SAS and other statistical packages, it has this built-in assumption that the covariance matrices are all the same, they're all equal. They have a common covariance matrix. And so in other words, cap sig sub 1, cap sig sub 2, and so forth, out to cap sig sub m are all equal. And if they're all equal, then we can just get rid of the subscript and we'll just denote that common covariance matrix by cap sig. Now, this assumption may or may not be true. If it's not the case that the covariance matrices are all equal, then we probably ought to be somewhat hesitant in using a procedure that assumes that the covariance matrices are in fact equal. Now, if we don't have another way, if we really do have to perform an analysis, if we have to get some results and we don't have another procedure or any way to perform a more general analysis that allows the covariance matrices to be different, then what we may choose to do is proceed using a procedure that assumes the covariance matrices are equal, but then issue a caveat when we write up our results. Say one weakness or one thing to be mindful of in interpreting the results is that there may be some evidence here that the covariance matrices are not equal. Now, because this is an applied class, it's beyond the scope of the class to delve into the mathematical details of how we actually perform a MANOVA. All right, it involves matrix calculations, manipulations, and things like that, matrix inversion, and so forth. But because this is an applied class, we're really not going to get into the mathematics. It's not our purpose to program these kinds of analyses or anything like that. We're going to rely on software. And so our focus is going to be using statistical software to perform the MANOVA analysis, and as well as any relevant follow-up analyses. And in particular, we're going to be using SAS Proc GLM to perform the MANOVAs and any follow-up analyses. So if, now this is typically for in doing analysis of variance, and I would suspect that if you if you think back to your first two methods classes, you probably did not use Proc GLM for performing analysis of variance because there are better procedures now, better procs in SAS, like Proc Mixed and Proc Glimix, that allow you to do analysis of variance in situations that you really can't use Proc GLM in, for example, mixed models. But one area where Proc GLM still is useful is doing multivariate analysis of variance because it's got the calculations built in. And so that's why we're going to be using it. All right, so again, we're not going to get into the mathematical details. We're going to use SAS to do the analysis. We're going to learn how to interpret the results, to interpret the output, and how to do follow-up analyses. And so what we've looked at here are the, what the hypotheses, the null and alternative hypotheses for the multivariate analysis of variance are. They're typically represented using vector notation, but we've actually drilled down and looked at the null and alternative hypotheses in more detail, going so far as to look at what those hypotheses look like expressed using the individual elements of the mean vectors. We've also looked at the assumptions that are built into a standard multivariate analysis of variance. And those assumptions are things that we need to be aware of and to watch out for violations of. In particular, let me go back to the previous slide. This assumption that the covariance matrices are equal may very well be violated in a given situation. And so, if we have a way to determine whether or not it's a reasonable assumption, we need to do that check really before we proceed with the multivariate analysis of variance. And actually, we're going to look at a way to test and see whether it's reasonable to assume that the covariance matrices are equal. But we're not going to get into that until we get a little bit further in the course. There's another set of analyses that we'll learn how to do, and as part of that set of analyses, there's a built-in feature that will allow us to test this hypothesis. But until then, we will just keep it in the back of our minds and realize that at some point we need to check to see whether it's a valid assumption.